So we've learned all that we need to learn in terms of new stuff for this unit, and now we're just going to do free body diagrams with a twist to put it all together. So the idea behind this is to look at some different scenarios that you haven't seen before and think about what can you do with some free body diagrams. For this video I want to enforce just a couple of things. First, I want you to be able to use vectors to draw free body diagrams and represent different forces that are acting on objects, and then I want you to find the net force on an object using a free body diagram. Now we've been calling this net force a couple of things. One thing is the resultant once you add up all of the force vectors together. And a way we've represented net force using a symbol is this Greek symbol called sigma and an F. Another way still is F sum or F net. The first example I want to look at is the example from our bell work. And in the bell work I asked you what forces are acting on this object that's being pulled by these men. First, hopefully you're able to see that since these guys are pulling this object with a rope, that force 1 is a tension force. And if tension is trying to pull this box this way, what should be pulling the opposite way is a friction force. Since most of our examples are going to be on Earth, this downward force is going to be gravity, and this upward force is going to be normal. And that should get you warmed up and ready to be thinking about all the different types of forces that we're going to talk about. So now I want to put some numbers to those forces. So here's another continuation on that example. It says, assume that the object is in static equilibrium. Hopefully something pops into your head when you read static equilibrium, and that means that the object is at rest. If F1 is 500 newtons and F2 is 4,500 newtons, then what are the magnitudes of F3 and F4? Now you have all the information that you need to answer this question, but it's being asked in a different way. And I don't want you to be intimidated by the language of this question. So let's just think about it, and let's label what's being given to us. First, F1 is this tension force, and it says that that is 500 newtons. Next, F2 is this normal force, and the problem gives us that this is 4,500 newtons. Now a key thing about this is it says that the object is in static equilibrium, and that means that the object is not moving, and the net force is equal to 0 newtons. Now that may be intimidating by itself, but think about what that's saying. A net force of 0 newtons tells us that this force has to be balanced by another force that's equal. So that pretty much just tells us that this force is 500 newtons to balance out the other one, because remember, equilibrium means balance, and this force going down has to be 4,500 newtons to balance that up force, that normal force. So in this case, the gravity force equals the normal force, the tension force is balanced by the friction force. Let's look at another example. Now I know this would never happen, so it says that you slipped while climbing, doing some rock climbing, and now you're hanging by a rope. So that's you. Your friend is at the top trying to pull you up. You have a weight of 500 newtons, and your friend is pulling up with a force of 1,100 newtons. So it's asking us to do a lot of things now. Draw a free body diagram of you showing all forces. Use vector addition to determine the net force, including direction. And it asks if your friend is able to pull you up. Now, a lot of the examples that we'll have now, free body diagrams or the twist, we're not going to be working with a picture. So I'd like to get rid of that picture. So, same information, but without a picture. So you have to use your imagination a little bit. And remember in the last video, instead of drawing something that's very complicated, because I'm not an artist, we'll just draw a dot. Now that dot is you. So what forces are acting on you? Well, you have a weight of 500 newtons. And we're going to label that as force due to gravity. And then you have a nice friend that's pulling you up by a rope with a force of 1,100 newtons. Now it might be tempting to call that an applied force, but remember, because it's a rope, I want you to think tension. So this is a tension force. And there's our free body diagram. Now to do this a lot more nicely, I should have used a ruler, and this should be more than double, the vector should be more than double for 1100 than it is for 500. It says use vector addition to determine the net force, including the direction. So for that, since these are going in opposite directions, we want to subtract them. And be sure to show your work for this. That way, if you have a math error, you can still earn some partial credit. So 1100 minus 500, you can grab your calculator, and that'll give you an answer of 600 newtons. But you need to be sure to put the direction, and that direction is going to be up. So this is for part B, and this is for part A. And part C says, is your friend able to pull you up? Well, since the net force is going upwards, the answer is yes. Your friend is pulling with a force that's bigger than your weight. Here's another example. This one is just talking about a block resting on a surface. It says there's a 2 Newton friction force to the left, and the block has a weight of 10 newtons. Draw a free body diagram and determine the net force on the block. So this is asking us to do two things. Let's do the first one. Draw a free body diagram. So here's our block, represented by a dot, or you can draw it as a square. It says there's a 2 Newton friction force to the left. And the block has a weight of 10 newtons. And that's going to be our force because of gravity. Now, if there's a friction force, that means that something has to be pulling. But this says that it's at rest. So, what this means is that there's going to be another force of 2 newtons on the other side. But we can't say whether that's a tension force or whether that's an applied force or what. So we'll just leave it as an arrow with 2 newtons. Now another force that's implied, but it's not on here, is going to be the normal force pushing back. And that's going to have a magnitude of 10 newtons. And that's going to be the normal force. So even though it only gave us the friction force and the weight, we can assume the normal force and a force that's pulling on the block or pushing on it, depending on how you're looking at it. Since this is at rest, that's a big clue that the net force, or sigma F on this, is going to be 0 newtons. And since it's 0, that's directionless. Let's move on to our last example. This one is talking about a book being pushed on a table. So it says there's a 25 Newton book, let's underline that, is being pushed to the right on a table with a force of 5 newtons. There's a friction force of 3 newtons. Draw a free body diagram and determine the net force on the block. Let's do it. Here's our book, and let's review the forces that are given to us. It says that the book has a weight of 25 newtons. That's going to be a downward force of gravity. It says the book is being pushed to the right with a force of 5 newtons. That's going to be an applied force. There's a friction force of 3 newtons. Now what's not given to us is the normal force of 25 newtons. But because we're amazing young physicists, we should know that. So now let's look at this. It says, determine the net force on the block. Well, we can look at the normal force and the force of gravity, and those balance each other out. So there's no net force going in the up and down direction. But if we look at the left and right direction, there's an applied force of 5 newtons to the right, and there's a friction force of 3 newtons to the left. Now we subtract that 3 newtons from the 5 newtons because they're going in opposite directions. And 5 minus 3 is 2 newtons. And we just need to say which direction it's going in. So we look towards the biggest one. 5 is bigger than 3, so the net force is going to be 2 newtons to the right. And we can say net force by drawing sigma F. Now it says, is the block moving? And we can tell that the block is moving because there's a net force of 2 newtons to the right. So yes, it's moving right. So that's our last example. Hopefully you're not intimidated by the wording, and hopefully this is a good way to put everything that we've learned in this unit all together. Now you're going to take a video quiz. If you're not ready, try to watch this video again or ask a question. If you are ready and we're not taking the quiz yet, go ahead and get started on the problem set.